a few things I need to clarify. So first, after grading the tutorial, the homework one, I found out that most of you guys didn't actually understand what's going on for the blocking and non-blocking. And I have this tutorial here shows you, I think that's task 2 here, all right? And I have an example sent just to some of you guys upon request. You can see that the reason I want to let you guys try this example is because it's showing you that why programming a hardware is different from programming a software, which is C++ or Python. I don't know if you feel the difference. It's very subtle, but So the C program, how that works. For example, you have a C++ code for the Arduino, and you download it to the chip. So Arduino, there's upload or download, whatever. So you upload it, okay? And then what is being programmed and how? Do you know what's happening there? Runs linearly, and it has a flash memory on the chip. That's why after you turn it off, the instructions are still there. So the flash memory is being stored, is designed inside the Arduino chip itself. So the C code or C++ code is being converted into a machine code, which are just 1 and 0s. If it's an 8-bit microcontroller, for example, here's a memory. The instruction memory stores all the instructions in the 8-bit form, okay, 8-bit, line by line, and each line has an address. And there will be an address decoder to take out every instruction one by one. So that's why you need a loop. If you want to keep blinking LED or keep running the same thing, you need a loop in Arduino. Okay, so that loop will be executed forever. It's going, after it's done with all the lines in the loop, it's going to come back because there's a instruction pointer. It's going to point to each line sequentially. So after all the instructions are being executed, it is able to come back to the top and rerun it. So you need a loop. Usually when you're running a microcontroller, you use a loop to keep that thing running. But definitely you have the if statements to make judgments of the signal being sensed from the sensor. But this is how that microcontroller works. So the Ipga program is different. An Arduino microcontroller already has all the digital blocks. I mean, it can be anything. For example, the GPIO pins, the SPI blocks, the I2C blocks, they are already designed and fabricated inside the chip. So that's the microcontroller, MCU. It's a microcontroller unit. However, for the Ipga, it's not empty. It also has all the digital gates in there, but they are not these established digital blocks. These are just the discrete logic gates, AND gate, OR gate, NOR gates, and you can use the different combinations of the already established gates to make different connections to form all the different kinds of logic blocks. So here's the difference. So Ipga chip only has general purpose gates floating there, and your program will rewire everything up and make a specific digital block. But for the microcontroller, everything is there already. It's just taking different instructions to let the MCU know what to do for the next step. But here's different. So whenever you are programming, you can imagine the Ipga is not taking any instruction line by line. Is that correct? You can design a memory file, but as long as you are not going to program a memory file inside the Ipga, there won't be any memory file, and you don't have any instructions. after you program it, boom, it's done. It's like a photo. You take a photo, and that's the entire digital block. It's not being executed line by line and sequentially. So that's why when you are programming FPGA using Verilog, you have to have that concept in mind. It's different. It's not being executed from the top to the bottom. It's like a picture. It's already like a mode. It's just being programmed and being wired up at once. So another question here is, if that's the case, why this sequential logic works? Why this one works? It's sensing that clock and then update the signal. So you have to have sequential circuits in there, or another way to say it, D flip-flops. Okay, you're having registers in there, so you can update the entire digital circuits using different states. It's a sequential circuit. So this example shows you that why it is different. All right, so you can see the this is blocking. If you look at the tutorial, so I think I showed you why they are different. Task 2. Sorry. Find out the location of it. So blocking is a sequential and non-blocking is concurrent. So whenever, so this is non-blocking, it's concurrent, which means at the clock rising edge, so pause edge means the rising edge of the clock. And it's going to assign all these things to the signals on the left-hand side at the same time. Concurrent at the same time. However, the blocking assignment, come back to here. So blocking assignment is sequential. It's doing one by one. So these are being implemented by registers. So the D flip-flops, if you can still recall your memory, like what are these D flip-flops? They have the previous state and the next state. And because of the time delay of the digital circuits, whenever it's being updated, it's just impossible to have the signal come back to the input at the same time. So for example, it's the D flip-flop like here. It's a D flip-flop. It has an input, has an output. All right. So before it, and it's only a positive edge sensitive. So the clock only senses the rising edge of the clock, which means it's only sensing the positive edge of the clock signal. So whenever the positive edge arrives, like that, when this arrives, it's going to send whatever here directly to Q. So this is D, it's a D flip-flop, the data, and here's the result. But after that, whatever you do for the D is not going to be sent to Q afterwards. It only sends the rising edge, keep in mind. And it's going to hold. All right. You haven't taken digital electronics, we're going to design D flip-flops over there. How to design the rising edge trigger D flip-flop. But not just need to remember it. This device can only update the output over here, which is called Q, that's the output, at the rising edge. Can you design the D flip-flop only sense the negative edge, the falling edge? You have to modify the circuit. It's doable. Yeah, we have been doing this a lot, but usually you don't do it. You know, it's very simple to do it here. That's why all the EDA tools are super powerful, because you don't have to, you know, for people who have taken digital electronics doing the VLSI design, when you are redesigning the whole circuit, just making it from rising edge to falling edge, it takes hours and hours, sometimes days, to modify the circuit. But here, only takes a second. So if you want to change it from rising edge trigger D flip-flop to falling edge trigger, just directly delete POS and change it to need NEG. So it becomes nag edge triggered. It's going to change the whole design of the circuit. Okay. So it is sensing always at the rising edge of the clock, do these updates to the circuit. So this is a concurrent assignment. It's going to assign all the signals to the left-hand side at the same time. But these ones are doing it sequentially because this is a blocking assignment. So it's going to assign X to Y3 first, even though you have a Y3 here, but it's not, because it only sends the rising edge really fast. Before this happens, it takes time to send the signal to here. But this already happens already. You know, the rising edge already sent the old Y3 bit to Y4. It's not being updated yet. So it has to wait for the next cycle to update Y3. That's why you are seeing here. Let's go back to the code again. So for Y, it's a 6-bit bus, has 6 bits in the signal line. And the first 3 bits, Y0, Y1, Y2, these are being assigned using the concurrent assignment or a non-blocking assignment. But for the Y3, Y4, Y5, these are being assigned sequentially. That's why if you look at Y3, Y4, Y5, it's only changes the rising edge of the clock. See? So the rising edge is going to trigger, it's going to send X to Y3. And it has to wait until the next rising edge here to send Y3 to Y4. And then wait for the next rising edge to send Y4 to Y5. Okay? But for Y0, Y1, Y2, they just happened concurrently at the same time. So another question, what are these values? Because it's a digital signal, only has 1 and 0. But if you want to represent any other numbers that are not 1 and 0, how? So like a bus. You just combine them together and make a bundle of it. And it's going to read. See here, this is MSB, this is LSB. That's why if you read it, it's 0, 0, 0, 0, 0, 0, it's 0. Okay? But for this one, 0, 0, 1, 1, 1, 1, it's F. You know, it's using the first 2 bits. So 0F is a hex number. So every hex bit has 4 binary bits in there, right? So that's why it's using the bottom 4 binary bits for the LSB hex bit over here, which is F. It's 1, 1, 1, 1. However, you don't have 8 bits in here. It's only able to use these 2 bits as zeros, and it's making zeros in the front by itself. So it's actually 4, 5, 6, 7. So these tools are not there, but by default, these are zeros. That's why it's showing a 0F here. For this one, it's 1, 1, 1, 1 for the lower 4 bits, so it's F. And for here, it's 0, 1. And it's making up 2 zeros in the front. It's not showing here. It's going to be 0, 0, 0, 1. So 0, 0, 0, 1. Okay, so that's why it's 1F. So this becomes 3F because it's 0, 0, 1, 1. And then 1, 1, 1, 1 is F. Okay. So this is some of the feedback after I graded your homework 1. And we're going to have a quiz during the lab. If you want to do it earlier, we can do it in this class as well, if you like. It's going to be 10 questions regarding Vim operation. I have 20, so I'm going to randomly give you 10 questions, and I'll see how I can do it. So it's 10 points for each operation. If you couldn't finish the whole command, but just 50% of it, I will just still give you 5 points, give you partial credit on that. I won't just totally take the 10 points off. And I'll let you know some of the examples really quick, what are I'm gonna ask you. Okay, that's for the quiz. Another thing, what's the other thing I will tell you? Okay, constraint files. Close this one. So I talked about that, I think, on Tuesday this week. But still, some of the students in the lab are still making mistakes on that. Let's just let you know, if you are following all the procedures in Lab1, it's going to show a different constraint files name. Go back to here. All right. Happened. Sorry. See this example. For the test bench, so SW and LEDs, these are signal lines physically exist on the Ipga board. And you have to, for whatever, there are all different versions of constraint files. So most of them are very similar. However, you have to double check to look at what are the names for the LEDs and switches in the constraint file. For example, here, if you download the constraint file from this website, maybe, I'm not sure, because there are many different versions and options. So the uppercase LED in this example won't work for the constraint file you have, because these are lower cases in the constraint file. I have to make the changes to the test bench over here to make it work. All right, that's the one thing I want to let you know. And another thing is on the FPGA board, all right, please, when you are working on this example, I recommend you do not use the ungate example here. So if you scroll up, you can find out this test bench is actually for the ungate example. The reason for that is maybe 3 years ago, somebody already programmed the memory chip on the board. So you are thinking like your bin file worked, but actually it's not. It's the code from 3 years ago, somebody else programmed into the memory file. So I didn't clean it up or reprogram it since then. So the only way you can demonstrate that your program in the bin file works is to use a different program. Just use the OR gate instead of AND gate here. So what this task is letting you to do is very simple. So it's actually making a little AND gate over here. I'll just show you real quick, intuitively. So what's happening? It's actually very, very simple. So for example, you coded up a module, which is AND gate, okay? And you download it here. So it's gonna make a little AND gate over here inside the chip, all right? And it's gonna assign, so the AND gate has 2 inputs and 1 output, okay? So you are actually making the connection, use the test bench to connect the 2 inputs to the switch, to the 2 switches, and then connect the output to the LED here. So that's why when you are turning on both of the, if it's AND gate, so you have to turn on both of those 2 switches in order to turn on this LED, because 1 and 1 is 1. Otherwise, if you have 0 in either of the 2 inputs or both of them, you are getting a 0. So that's how you can verify the AND gate, AND logic. First, there are 2 ways to program the Ipga board. So follow the procedure in the tutorial. So first, you just simply connect the USB cable to your computer, and it's going to generate, after you run the bitstream file, which is creating a bit file, which is here, see it's the dot bit. After you run all the procedures, it's literally just a click, 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 next, next, next. So it's gonna synthesize your file, test bench, and also the module, and eventually generate that bit file, which will program your FPGA. Open the new target, it's gonna open the FPGA board, and it's gonna be programmed. All right, it's a very simple procedure, and it's gonna program your FPGA through the USB. However, if you turn it off, it's gonna disappear. If you turn off the board, here use the switch and turn it back on, it won't work anymore. Okay, which is bad, right? Even though it's not a microcontroller, usually the Arduinos, you program this thing stored in the flash memory. You turn it off, turn it on, it's still working. That's what it's supposed to be. Okay, but this one is different. So how can you make the board to memorize your program? So I showed you the example in the lab. So the secret is over here. And the file name is not a bit file, it's called bin file, .bin. And the tutorial shows you how to generate that bin file. So you have to upload that bin file, just follow the procedure to upload the bin file, and it's being uploaded to where? To the bottom of the board. I don't have a bottom view of the board, but at the bottom, there's a memory chip. It's IC. So it's an integrated circuit chip, it's an IC chip. And it's able to program that IC chip. So whenever what you want to try is you want to turn it off and turn it back on, see if the AND gate is still there. That's how I can verify it. Again, don't use AND gate, use OR gate, because probably somebody else already programmed using AND gate 3 years ago, so it's still in the memory chip. And how to do that? Follow the procedure. It's literally just reconnect the jumper wire to the top. So shorting this, if you look at here, it's a QSPI. So the memory chip at the bottom is being connected to the FPGA chip using the SPI protocol. So it's actually programming this FPGA using the SPI port. And you have to reset it or reprogram it by pushing this push button here to program the FPGA. If you keep this jumping wire over here on the top, it's going to keep keep the memory chip communicating with FPGA in real time in the future, as long as you part it up. Just keep in mind, if you keep this jumping wire here, you will try it, right? So just think about you are the customer. You have a product, even though it's a very simple gate, just OR gate, and you are not going to upload the code again, program the board again, right? You just program it once, store the bin file in the memory chip, and you part it off and turn it back on, see if the OR gate is still there. That's what you are expecting, because any of the consumer electronics, you turn off and then turn it back on, the program should still be there, right? It's a evaluation board. It's not a final product. However, usually the developing procedure is you verify everything on the development board, because you don't have to design the USB port or design the VGA port or design the circuit by yourself and make into a PCB, which takes like a couple months, and then trying to optimize your design. It takes time. That's why this kind of evaluation boards are really sweet, because you don't need to connect everything by yourself, just program it. But eventually, for example, a company is asking you to design the product, but using this FPGA. You just need to go back to their data sheet, look at their schematic and layout, see what are the components are required to let it work for your project. For example, the SPI memory, right? You want to keep the code, the instruction in the memory file instead of losing them. Just go back to their schematic, looking at their connections, and make your own PCB board. That's how that works. All right, so I think these are the things I want to let you guys know, and we still have time for the class. I will be here. You can work on anything you like, Or if you want to do the quiz now, just let me know. Only takes like 3 to 4 minutes, 5 minutes or less. And you are going to work on Lab 2. It's working on the OR gate, implement the OR gate to the FPGA board, program it using USB, and program it use a onboard memory chip. So that's literally everything for the lab. And if you do the quiz now, you don't have to come to the lab in the afternoon. I will be there. If you want, you can still come. Okay. Any questions? Anything? Clear?